Okay, for people joining this live stream, we are starting a little later than expected because we had a very exciting discussion among participants of our summer school about essentially the physicalization of meta-mathematics. We'll come to that another time. Okay, we have a bit of background noise here, by the way. Okay, so our discussion here is about local multiway systems. So I can let me just this is equivalent to resource function of Wolfram model, right? Max?
Yeah, if you updated the packlet, then it will be.
Hopefully it will update itself. Let's just see.
Yes,
Okay.
you need to run packlet install of set replace as it tells you in the error message.
No. Why isn't that part of the update for this? Why can't I just do that by updating?
Well, because there's a vastly simplified way it works, so it's more stable, which essentially uses a packlet directly instead of loading from resource function notebook. And because of it, since we cannot just update the packlet without user's permission.
Okay, so that didn't work. Oh, set replace doesn't have a backtick.
Okay, here we go.
Could you ask Roger to make sure this is done on all my machines? What is that? That didn't work. How come?
Can you just try it without resource function first?
You mean just the, but I won't have it defined. Oh, it's in that. No, that didn't work either. This is a little disappointing. I thought we would have made sure that Roger had this set up.
Can you run get set replace backtick, because maybe it's still the previous version.
Okay. Well, this needs to get unscrambled. And I mean, for people who just update the packlet, right? I mean, for people like at the summer school who are just updating the packlet. I mean, I'm sorry, just updating, just typing in. I mean, so let's try this here.
If I assume it would work now. It's right, because it now just calls the packlet. It doesn't do anything else anymore.
Okay, fine. Okay. So our subject is local multiway systems, and
yeah, this one is not local yet, and you can see it picks one event and it doesn't pick the other one because it overlaps.
Sorry, something very strange is happening here. What's happening here? I don't understand why that's doing what that's doing. Yes, I will increase font size. Sorry about that. But first I have to debug why this isn't saving the file. Let me check what version I'm running here. It's a nice sober version. What is going on here? I am totally confused. Is it putting up the dialogue? Okay, I'm gonna exit this because something is just way too confused here. Okay, let's try starting that again. And yes, I will make it nice and large. And I want to do this with resource function. By the way, we should add to our introduction to this technology, these things. Okay, so let's just check this. Now I want to check. Okay, that's much better. Local multi-way systems 01. All right. All right, so let's have an introduction to what's going on here. So this is the expressions events graph.
Right.
So,
and this is still global space-like evolution, not...
Right, let me use as an example the thing I've been using as my sort of standard, fairly complicated rule. Let me just because I understand that one a little bit. Hold on a second. Let me just pull it in. Okay, so there's our rule, and let's start it off from, I can just say automatic here, which will start it from the simplest thing, and then I want to say comma 3, for example, and then I want to say expression events graph, right?
Expressions events graph.
Okay, let's try to understand what this is. Okay, so the initial condition contained 2 expressions, 1, 1, 1, 1.
Right.
Those were combined in a single event. This is a useful graph. It's combined in a single event to produce 4 expressions here.
Right.
Okay. So this is a particular, this isn't a multi-way graph yet. This is just a particular evolution path, right?
Yeah.
Where those 2 events, those 2 expressions were combined in this event, they produce 4 events, etc. Great, dandy. Okay.
Right.
So if I were to run this longer, okay, so this graph normally is producing, this is kind of, what kind of a graph is this like in our previous, there's like the pictures that we made.
It's just with additional vertices inserted inside the edges.
Okay.
So for a single way system, it doesn't actually give you any new information. You can get the same thing by labeling edges.
Okay, this is just the causal graph, but with its edges labeled by expressions.
Or a global multi-way evolution causal graph where the evolution states are split up into edges.
Yes, right. Right. Where each bucket
which is a very
here,
non-trivial process, but essentially, yes.
Right, by making, okay, so let's look at this one here. Okay, so that's this here. Okay, so this is to be compared with the causal graph, which looks like that, which is the
Better to use layered causal graphs so that it's more consistent.
Happen to be the same in this case, but okay. But so this is showing the same connectivity of the events that we were seeing before, right?
Yeah.
Okay. Now, Jonathan has said this is like a multi-way graph. Why?
No, I'm saying it's like it's the evolution causal graph for a single path in the global multi-way.
I agree. Yes, I agree with that statement.
But with the states split up into hyperedges.
Yep, I agree. Now, just for my interest, in the strings case, what is the analog of the expression events graph?
Oh, you split a string to characters. It's like those evolution plots you're doing with shaded regions in between.
Right. So we have an analog of this. Okay. I mean, what is the name of that function? And I think we have that in the function repository.
Multi-way evolution plot.
Is that what it's called?
Yeah. And I set it up. It takes the same arguments as multi-way system.
Wow, you cleaned
Why
that.
is it multi-way?
Because string substitution systems are multi-way systems in general. They like.
Okay, so we say BA goes to AB here.
There isn't a canonical updating order on strings.
Okay, so let's take this. Okay, so now what's this here? So can I?
You can do the positional polygons thing.
How do I do that?
I think it's is it event rendering? Oh, I forget what I call the option. Wait, evolution event rendering arrow positional polygons.
Well, it's not the same thing because vertices here are entire states, not single characters.
Right, but if you split them up into elements, then it would be an an expression.
Well, except some of the elements
positional polygons
the same, and it shows them in multiple different ways. I mean, it splits them up if they're in different states, even if it's the same character. So just splitting them.
Well, there's no notion of. I mean, these characters don't come with kind of labeled with the. It's not like the expressions where every element is unique, so to speak.
Sure, they come labeled. You can construct a labeling from the event.
Well, each character is unique. You can keep track of how it goes from one state to another. The problem is that here there's duplication going on because the same character appears in multiple states.
Mm-hmm.
Right.
But so then that's just the situation where there are multiple events going in and multiple events coming out from the same character.
Well, okay, these pictures are.
But it doesn't have duplicate them.
Okay, these pictures are as yet somewhat different because this is very definitely a multi-way graph.
Yeah, the one below is a global multi-way system.
I know. All right, so let's start looking at your local multi-way. Okay. Okay, so let's look at this now in the local multi-way case. What do I do to get that?
Event selection function goes to none.
Okay, I don't completely understand that yet, but let's find out what that means.
I mean, you don't select events, you use all of them. In other words, in the previous case, some events are skipped because it only does one single evolution, but now it doesn't skip any events. And it would grow very quickly, so, right.
That feels like it should be identity rather than none.
Why identity? What do you mean identity? It's a selection function.
Right, so your selection is everything, is the whole list.
I agree that doesn't seem quite right. That it sounds like you're selecting nothing.
Right. It should be consistent.
Oh, you're saying it should be all.
Yes, that would be even better. Okay, so
fair enough.
Let me understand what this did here. So this is the same as we got before, because there was really only one possibility.
Actually, it's not the same. It's because you can match these ones in two different orders.
I see. I see. Okay. So if I now go 2 steps, and let me forget the vertex labels because I think that makes it absolutely hopeless. And I probably also want to, okay, let's do this. Oh, another one of these incomprehensible pictures. All right, let's do this. Okay. Somehow this reminds me greatly of one of these, connectionist networks and neural nets and so on. Okay. So these are the expressions up here. Those are the events. Those lead to more expressions here. Oh boy, this is complicated. Okay.
Yeah, one problem is that it has somewhat unnecessary duplication, because if it can match two edges in different orders, even if they're identical, it's going to produce two identical branches.
Okay. So let's see. You have some other options here. What other options?
Well, not yet, but that's something that would probably be useful to have.
Right, but I mean, so here, let's try to look at a causal invariant. Let's try to look at some simpler rules here. So let me just pull up some simpler cases. For example, I want to look at a causal invariant rule. Maybe that's not going to be very useful, but let's try taking a look at it anyway.
Well, if it's non-overlapping, it would produce exactly the same result. If it is overlapping but has trivial pairs merging quickly, then it would produce a different result because it doesn't do isomorphism.
Let's try doing this one.
Exactly. I don't think you can see any signatures of branch pair resolution without isomorphism testing.
So wait a minute. Let's try doing this.
Oh, this one is non-overlapping, so it would give you exactly the same result.
Why isn't it? Okay, hold on a second. No, I don't understand. It's just making a tree here. Is that your comment about the fact that it can't? So how do I get back to this then?
Well, of course it's a tree. It takes an edge and it splits into two at every step. So it's not even a multi-way system. It's just,
okay,
just
but the merging that we see here is not happening because we're not doing isomorphism testing. Is that correct? I don't understand how this global isomorphism.
These are states, so the merging there wouldn't even make sense in local multi-way system.
Okay, so what's the analog of that? How do we see causal invariance in a local multi-way system?
Well, here it's obviously causal invariant because it's non-overlapping. There are no branching of any kind.
What do you mean there's no branching? What are these branches?
Well, they're not branches. They're events creating multiple edges.
Okay,
so the way you can see it, if you look at blue vertices, if blue vertices have out degree at least 2, then there is branching going on.
Okay, so in other words, a branching event, and I'll put it in quotes, is seen in the branching of a state vertex.
Yeah, it's not an event, it's at least a pair of events.
What are we going to call that? A branching moment.
Wait, sure, I mean, it's a branching edge, essentially.
What does that mean?
Well, it means that edge can be used in multiple events.
Well, I understand that. A branching, but what are we going to call that elementary moment of branching? That elementary
evolution ambiguity.
Right. Wait, it's a branching.
It is a branching. It's going to lead to branch-like separation. The things
why don't you like the word branching?
Because I want a noun. A branching. Well, you're saying a branching is seen in the branching of a state. A branching. Okay, it's somehow that okay.
Well, you know English better than me, so I can't argue about it.
It only sounds silly because you're saying it in a silly voice.
Okay, all right. A branching. Well, okay. So, but the basic point is, as we look up, so an event, a splitting at a state vertex is quotes a branching.
What is a state vertex?
One of those.
There's an edge vertex or expression vertex to be consistent.
Okay. All right. Splitting expression vertex is a branching. A splitting at an event vertex leading to branch-like separation, right?
Right.
Okay, a splitting at an event vertex like this leads to space-like separation. Is that correct?
Yeah.
So what do we call that? A splitting at an event vertex. What is that?
Well, generally events would do this unless I have a single output.
But the main point is, this is the distinction between branch-like separation and space-like separation, is two things that we see are space-like separated if their common ancestor, test for branch-like versus space-like separation is the most recent common ancestor.
Why most recent? Oh, you mean the one, the first intersection point?
Yes. Most recent common ancestor is is expression versus event vertex, right? That's the criteria.
Oh, essentially, there's subtleties to this because there might be multiple most recent common ancestors.
Okay, well then it has both branch-like and space-like separation.
Yeah, pretty much.
Just for my sort of generalization instinct, what is the Rulial analog of this?
Well, we have multiple rules.
No, I understand that, but so how do we see what is Rulial separation in terms of this?
Well, if the same edge would have two, if the same expression would lead to two different rules. So from an expression vertex, we get edges going to event vertices. If those event vertices correspond to different rules, that would be that Rulial separation.
Okay, but so just to understand, if we go backwards from a given, what is the analog in this story here of going backwards to an expression event to an event vertex? What is the analog? It's to an expression vertex.
Yeah, it's a splitting at an expression vertex, which leads to events. With
right. So Rulial separation, common ancestor. Oops. Ancestor. Is an event is an expression vertex, expression node, expression vertex, whose successor events correspond to different rules.
Right. And by the way, if you say vertex labels goes to automatic in expressions events graph, and you have multiple rules, it will label events with a rule number.
Okay. So can we do this, by the way, with? We can't do this with Turing machines. This isn't a. Or we could do it.
Oh, we can emulate them.
Yeah, but it's pretty complicated. I mean, it might be worth doing that because we kind of understand what's going to happen in a Turing machine.
Well,
So
Turing machines are not that complicated to emulate.
okay, we'll just do it. So are any of these, okay, here's a rule. This is a rule which is causal invariant, but has a multi, okay, so let's look at this case here. Let me not do it for as many steps because it's going to get really complicated, I suspect. Let's just live modestly and let's just do 2 steps. Okay. Let's do 3 steps. All right. So now what is this and what is going on here? Oh my gosh. You know, these things become very complicated very quickly. Have you noticed that?
Right.
That's what you get. The universe is a complicated place. All right. So now what's going on here? So this is the initial event. The initial state has 2 expressions. It has an event. So now, if I were to knit together, I want to knit together the story of this, the space-like story of this. So I'm trying to make multi-space out of this. How do I knit together a piece of multi-space from this? Do you understand my question? So these things here are space-like separated here, right?
Yeah.
This thing is branch-like separated to that.
Right.
Right? So in a sense, this picture is the inverse of what we want to build a picture of multispace. Because in a picture of multispace, what we want to do is concentrate on space-like separation, treating branch-like separation just as sort of bubbling up in a different direction. If that makes sense. So we'd like to take this.
That's one way to do it. But I'm not sure it would be simpler to understand.
Well, that's the point. We understand space better than we understand branch-hill space, is my claim. Because what
the question is which one is larger?
Branch-hill space is certainly larger.
Right. So, I mean, it seems to me that it would be easier to understand if we have multiple space-like sets, and then the branches are kind of separate.
I don't think that's going to be easier to understand, because what we want to understand is, you know, quantum mechanics as an afterthought, so to speak, which means most of the time we're looking at physical space motion, but quantum mechanics is just sort of an orthogonal afterthought, so to speak. That's what I was hoping we would get from this. I mean, let's look at the analog in let's see, I had started trying to make some pictures of multi-space with Turing machines, and maybe we've got a better way to do it with this. Let me bring up.
You're assuming branches don't diverge macroscopically.
Yes.
Which is not obvious to me.
Well, I mean, eventually they presumably do, but hopefully they don't immediately, or we wouldn't imagine, you know, we wouldn't perceive kind of a pseudo-classical world.
But that's what we disagree with. It's a many worlds interpretation versus a kind of traditional interpretation with measurements. Because in many worlds interpretation, you can have very different branches.
This is required for violation of Bell's inequalities.
What is?
That nearby branch-like separations can yield arbitrarily non-nearby space-like separations.
Nearby branch-like separations?
You're arguing that you can visualize these things using multi-space picture because if 2 events are nearby in branchial space, they will be correspondingly nearby in physical space.
No, I'm not arguing that. I'm just arguing that it will be easier to understand because we're much more used to moving around in space than in branchial space. That's my only argument. I mean, it's just for us poor humans.
Yeah, but so how can you make, maybe I'm misunderstanding, how can you make a picture in which the branch-like separation is an afterthought to the initial space if the branch-like separations can yield arbitrary space-like distances.
Well, you'll certainly have things that connect arbitrarily space-like distant, in that branchial direction, you will have, I think it's just a question of how the visualization works and how important that phenomenon is. If the whole thing is covered with that, then yes, it will not look very good. The hope is that won't be the situation. Just see here. I seem to have a lot of multi-space pictures. What are all of these? That's not very useful. I think I had some attempts to oh yeah, what about the branchial graphs of this? What is the analog of a branchial graph in a local multiway graph? Do you understand that question?
Yeah. Well, it's it's a question of how we select sets of expressions. So to get a space-like state, we are just selecting maximal subsets of expressions which are pairwise space-like. But we can also select subsets of expressions which are pairwise branch-like, for example, or some mixture of those.
All right, so let's understand how we would extract from this a spatial graph, a sequence of spatial graphs from this picture here.
So the first step would be, is given two expressions, identify what the separation is between them.
I'm sorry, say that again.
The first step would be to take two expressions and identify what is the separation between them.
In space-like separation, you're saying, or branch-like?
Space-like, branch-like, or time-like.
Yeah, okay. Okay. And so then what? So then what we're trying to do is make maximal collections, for example. Maximal space-like collections are a possible spatial graph, correct?
Yeah.
So, okay, so spatial graph equals a possible maximal space-like collection, maximal collection of space-like separated events, expressions.
Right.
Okay, so let's look at how that would work. So what we're saying is we have the question of space-like or time-like separated. That's a relation. So given a set of expressions, given a set of expressions and events, we have certain relations. We have a set of expressions or a set of let's see. Yeah, right. So given a set of expressions, right, we can ask, they have a collection of binary relations. They're binary relations that say separation is, time-like, space-like, branch-like, right?
Right.
Okay, so then what we might do, okay, so let's look at that for this case, for these expressions here. So let's look at that bucket of expressions and ask what their relations are. So every expression here, so if we label these expressions here,
if you don't care about atoms they have, then you could just say vertex labels goes to name. You should just give numbers. Because here there could be duplicates.
How could there be duplicates here?
Oh, because they're atoms. So if the set, I mean, if the list of atoms is the same for multiple expressions, they would have identical label.
Okay. So those are
Just
the
indices.
unique names for each of these, right? So
Right.
for every pair of expressions, we should be able to decide whether it is time-like, etc., right?
Right.
So do you have code that does that, or should we write this?
No, I don't have that code yet.
Okay. So in a sense, the reconstruction of a spatial graph is like an anti-chain. Is that correct? I mean, well, except this is not a partially ordered set. What the heck is it? Let's actually get that collection.
Well, why not? It is partially ordered set. It is a causal graph.
But isn't it the case that the relation, isn't it a symmetric relation? If two things are space-like, if A is space-like separated to B, then B is space-like separated to A.
Well, yeah, the relations are not a partially ordered set. The causal relations are partial order, not separation ones.
Brian is making comments about saying a branch makes it easier to imagine way off parallel, but a branch is a fish tank of space. Oh boy. You know, this stuff is really hard to understand. Okay, so should we write the code that just finds the relations here? Is that easy to do?
Well, it's not too hard, I think.
But is that useful? I mean, so in other words, in the general case, what we're going to find is, see, this is what's so difficult. I mean, we've got different. Okay, think about foliations in this context.
Okay.
Because I don't understand how to knit together a single foliation, because there's going to be partial orders between. Oh, I'm so confused here.
What do you mean? What do you want to do?
Oh, that's an interesting idea from SWSH. Make a rank 3 tensor of distances, time, space, and branch between all expressions. That's an interesting idea. Let's just do it, right? We should be able to do that, right? There's a notion of okay, what is the space-like distance? Let me just do this as an exercise. What's the space-like distance between expression 7 and expression 8?
Well, you would need atoms then. So, well, they're actually both 1, 3. So the distance would be 1.
Why?
Well, because they're connected by vertices or atoms 1 and 3. So to go from one to another, you just traverse one vertex.
Explain.
Well,
So
if by distance you mean distance in a spatial hypergraph.
Yes, I do.
Then, well, that would be distance between hyperedges, not distance between vertices, but it's not too different. So these two hyperedges have two shared vertices because they're both 1, 3.
Yes.
And so distance would be 1.
Why?
Well, because you go from one to another through a single vertex. It's like if you have two vertices that are connected by an edge, the distance between them is 1.
Yes.
So if you have two hyperedges connected by a vertex, the distance between them is also 1.
Oh, I see. So it's the dual graph, effectively, the dual hypergraph.
Yeah.
Okay. So all right. Okay, we can also just measure the distances, I mean, in my crazy, BTX distances, basically, right? That's what, so we should be able to get the BTX distances between every two expressions, right? Where the X distance.
We need to determine which. Right. Okay. If the expressions have shared vertices, then it's easy. But the problem is if they don't, then we need to decide by which state do we measure the distance, because in different branches the distance could be different.
Well, we want the geodesic distance. We want the shortest distance, presumably.
Yeah, but by using which expressions?
Wait a minute.
There are multiple states. So these expressions could both exist in multiple states. And even if they're space-like separated, there might be multiple branches in between. So the path from one to another would depend on the branch you're in.
Okay, hold on. The path from one to the other might depend on the branch. Yes, that's clearly true. I mean, that's just saying that there are different forms of space in different branches.
Right. So one notion of distance would be just take all expressions from all branches and all times in history and compute distance there. But it wouldn't necessarily be what we expect.
No, it would not be. Well, so what is the space-like distance between expressions?
So why do we need space-like distance exactly?
Well, because we're trying to lay things out. I mean, we're trying to lay this out in. Look, we're trying to lay it out in multi-space-time, basically. Right? That's the goal.
I see. So you want it for visualization purposes?
Yes.
Because if you want it for physics, then I would imagine what we should actually do is to measure distance between events or trajectories by sending geodesics from one to another. Kind of like light signals.
But they're not light signals because they go into different branches, right?
Well, if there is a path between them in a causal graph, that means they're not separated enough so we can still communicate between them. But if they are actually in different branches and they never connect afterwards, then there's no distance between them. They don't communicate.
Okay, but I want to come back to this question about convergence. I mean, in this graph here, I see we are starting to see convergence. Okay, what does it mean? This graph has global causal invariance, with respect to the global multiway system. How do we see causal invariance in this case?
Well, that is unclear because we don't necessarily know what it means in this case. So
well,
causal, I mean, to be honest, I don't even understand what causal invariance means in a global case, because the definition is that the causal graphs are the same eventually.
Yes.
But if they're infinite, I still don't understand what it means for them to be the same.
Well, that's complicated, right? Jonathan, are you with us here, or?
Yeah.
Do you have any thoughts about causal invariance for local multiway graphs?
Well, without isomorphism testing, it's not immediately clear what it means.
Well, so let's try and merge these ideas.
Yeah, so one thing...
Yeah, that's what I'm working on.
I mean, we could have a kind of confluence in where we say, well, it should work essentially the same way. If we have two expressions on different branches, then either is a path from them to a single expression in the future.
By the way, in this picture, were there any branch-like matchings here?
Yeah, because the same expression has multiple outputs. I mean, multiple outgoing edges.
Well, but wait a minute. I'm saying, were there matches that happened between different branches?
Oh, I see. I don't see that here.
Should we
No,
try
I don't
one
think so.
step? I mean, but
well, we can.
What will that look like when there is a thing between multiple branches?
Well, two branch-like separated expressions go to the same event. It doesn't look like it's happening here. I don't think it's happening here.
Okay, well, should we try a different rule? Where, okay, a couple of branches here. One is we could try the Turing machine rules. Should we do that to see whether there's something?
Okay. I mean, if it's deterministic Turing machine, we wouldn't see anything interesting because it would be the same as single-way system, but we can make it into a non-deterministic Turing machine.
Well, okay, but do you think that's going to be reasonable? I mean, in other words, because that's at the minimal case of branching, right? Am I making sense? A non-deterministic Turing machine is like the okay, so this is a Turing machine. So, well, let's see, where's the Turing machine compiler? I don't know whether it's in there. Okay, so let's say oh, fluffle.
Well, that's just a state, so it doesn't give rules yet. We need to copy another picture. Yeah.
Oh, that seems to have the same thing for the encoding rules.
Yeah, so encode TM rule is all we need here.
Okay. All right, so let's encode the rule. Let's encode one of the 2506 rule with the 2.2. Okay. Oops. Why doesn't that work?
It might only support 2.3. Not...
Oh, you can't be serious. You cannot be serious. Well, that's a bit embarrassing that it only supports 2.3, but okay. But so how will we make it non-deterministic? If it only supports 2.3, by the way, we should definitely write the code for the general case. Okay, but so how do we make it non-deterministic here? So we've got this one.
Well, we need to combine some of those rules. So if we make this system of rules for two of them, we can just merge them afterwards.
Okay, let's take this thing with this one here. Okay. Now what?
Well, we can just join them. Yeah. And we need to make sure we remove duplicates, which I think we will, because variable names seem to be the same. Yeah.
Okay. So let's just, should we make a rule plot here just to check?
Sure.
let's call this NDTM.
Okay, here's one more rule which is reasonable.
That's encouraging. Okay, all right. So let's try running this. So let's try running the deterministic Turing machine first, right? In this case, okay?
Okay.
And what do we have to have for the initial state?
Well, we need to use encode tm state function.
Okay, so here,
That's not the state.
No, this is the state. But what should I do? Should I just have? Let's just do this, okay? And so then let's say 1, 4 there. What's that? There it is. Okay. Actually, I could just have a blank tape. Let's just do a blank tape. Okay. Happy, happy?
Yeah.
Okay. Actually, that was just the, now what the Turing machine encoder, okay, so that's where we wanted this thing here. Okay, that's
right, encode tm state.
I think there's some debracing to do here. Okay. All right. Okay, that's the encode TM state. So then we want to say NDTM rule and here we'd say encode TM state of this. Oh my gosh, what is it doing? What is it doing?
Surprising it is that slow.
It's surprising because it should be deterministic.
But it's not deterministic, it's NDTM rule.
Oh, I should have done, oh my gosh. Well, I don't know where I killed it here, but let's do the ND, let's do just the deterministic rule first. Okay.
Yeah.
Let's just do our friendly deterministic Turing machine rule for 2 steps. Oh, come on, what the heck is this?
Can you try to just do causal graph?
Right, why don't I just do, yeah, okay, fine. I could just do 1 step, but I could also just do causal graph. Okay, where do I do that? Here.
Yeah. I'm wondering if there are multiple orders to match those rules here again, which is...
That does not look promising. There should just be a single path in the Turing machine, right?
Yeah.
You know, it may be that the encoding that you had there is just a max scan, you know, only works for the max scan ordering. Is that possible?
What do you mean by max scanner? You mean...
But this encoding here.
Automatic coding.
Oh no, that's right. This is
well, it shouldn't, but
no, but
sure.
This was only sensitive to. I mean, in that case, there, that causal graph.
Well, one problem we would definitely have is that you can extend the boundary. Although I thought I fixed it at some point. So extension of boundary was done on demand, but I don't know if it made it into this document.
Yeah, you did.
Not.
No, I'm pretty sure it did.
Okay, then it is strange.
Well, so, okay, a bit of debugging is needed there. But so what we hope we'll be able to see there is in this attempt to understand the Okay, so what we expect, so a couple of things. So we need to debug this Turing machine thing. We also need to debug, or we need to construct something where for every pair of expressions, we can assign it. Well, you say this is kind of meaningless. The space-like distance is kind of meaningless because it is contingent on essentially the branch-like. Look, if the thing has, I'm so confused. If it's in the same branch, so it has 0 branch-like separation, then it has a meaningful space-like separation, right?
What do you mean it's in the same branch?
I mean, it is not branch-like separated. Two expressions that are not branch-like separated.
Okay. But if they're space-like separated, it doesn't mean that there is only a single branch in which both of them exist.
No, I understand. Oh boy, this is head spinning.
Well, it makes a lot of sense. If you have classical evolution in 2 regions of space, but then in the middle you have some quantum stuff going on, then the distance between those 2 regions would change because you would have to go through the,
Quantum stuff
region.
in different ways.
Well,
Okay.
you would have multiple branches in the middle with different configurations of space in them.
Look, let's see. I forget who was working on this project. Was it who was working on the project of trying to Hatem? Okay, yeah, that's what I thought. Of trying to understand kind of double slit-like things in the context of both the local multi-way system and the completion interpretation in a global multi-way system.
Yeah.
Again, let's walk through. So Jonathan, do you think you understand that correspondence? So
yes. In fact, I'm about maybe 20 minutes away from having an implementation of local and global in the same framework.
Impressive.
Maybe. I don't know. Just at least in the strings case.
The question is whether the geodesic and rullial space that you're on is really a 20-minute length. Never mind.
It's undecidable.
Right.
But yeah, I mean, so all that's happening is that in the case where you have 2 branch-like separated edges in the local multi-way system, and they're being ingested into a single event, that's the case where there is effectively a completion rule that connects those 2 branch-like separated edges in the global multi-way system, and therefore allows a single state to be ingested into a single event. It's just, so the only difference is that one of them is doing the completion at the level of the events, and one of them is doing the completion at the level of the states. But they're doing the same thing.
Okay, doing the completion at the level of the states is the global multi-way system with its completions, right?
Yes, right.
Okay, what do you mean by doing completion at the level of the events?
So what I mean by that is, how do you take 2, the local multi-way system, as I say, its main distinction from a global multi-way system is that it can take 2 branch-like separated expressions and apply a single event to them.
Yes.
And so, in effect, what you're saying is we're going to treat those 2 branch-like separated expressions as though they were equivalent in the sense of as though they were on the same branch of history in the global multi-way system.
Yes.
Which is a completion.
Well, it should correspond to a completion.
Right. And I'm hoping we should be able to...
I mean, it's not clear why it would be the same in general.
Well, it depends on, and both have some choices to make, like which completions you make. There's some arbitrariness in the choice of completions. There isn't just one set. I mean, it's like different foliations. You can make different choices of completions that will all lead to the same sort of forcing of causal invariance. we should probably wrap up in a minute here, and I know Jonathan has to go. And some of us are hoping to go to the hangout for the summer school. Oh boy. Well, there's much more to say here, but I think I mean, Jonathan's merged global, local, multi-way thing. How are you doing that? Are you doing that in the context of the multi-way system function or what?
Yeah. So all I'm doing is, because we already have a way of canonicalizing states to events, right? I mean, that's the Max. I mean, correct me if I'm wrong, but that's the main algorithmic problem here, is making sure that when you have duplicated states that come from the same event, that they're treated differently, or come from different events, that they're treated differently, right? Multiple expressions that come from the same event.
Well, if you don't do isomorphism, that treated differently, right?
Right. So
what does it?
So my point is, we have a way. The global multi-way system does that using the state IDs, and from the state IDs, then you can construct event IDs, and vice versa. So what I realized was you can just take the states, split them up into expressions, marked with those IDs, and then evolve the thing like it's a local multi-way system, but using the global multi-way framework.
How would you do that using global multi-way framework?
Well, by applying, just by doing it. I mean, you just apply completions at the level of states rather than at the level of events.
I think this is one of these we have to see the code.
Do you have, so the states graph would still have entire states in it? Is that
no, it would have expressions,
but then
canonicalized using state
how
IDs.
Can you have two because in the global multi-way system, each event only has one input, but it starts from a single state. So how would you have an event with two inputs?
Hang on, wait. Let me give me one moment. I can share my screen in just a second and explain what I'm doing. Okay, here's what I'm constructing. It's almost done. Oh, oops, sorry. I'm videoing, not sharing. There we go. Okay, so this is a string multi-way system, a very simple string multi-way system with just space-like events, space-like separated events in the normal global multi-way case, right?
Okay.
Mm-hmm.
This is the associated thing in my currently very hacky and only working for space-like separated local multi-way system implementation. So now you can ingest a pair of expressions, which could either be space-like or branch-like separated, into a single global multi-way event.
Okay.
And so each of the expressions is canonicalized by its step number and state ID, and that which is then consistent with the event number and event ID, because we have a scheme for doing that. And so I think, unless I've missed something, this implementation should end up being equivalent to yours.
Except that here you've aggregated Max's localized events into one global event.
Yes, right. Which you can do because you can do because you can effectively merge states and events based on state and event isomorphism.
How do you know the rest of the state? The rest of the state is not deterministic in this case. Because the rest of the state,
he's just starting with a tiny state here. I mean, it'll build up to a bigger state, and then his global events.
These events are all local.
No, but his events are global here.
Why?
Right, because they specify the remainder of the state. Yeah. If you look at the event list, right? I mean, that's.
But how do they know the remainder of the state? Because the remainder of the state could have multiple branches in it, independent from that branch.
Yes, yeah, exactly. So the rest part of the event in the global multi-way specification can't just be an expression. It has to be the whole expression's causal history. Because yes, you could have multiple branches that yielded the rest.
Right. So in other words, the global events are essentially all possible consistent sequences of local events.
Right. Exactly.
Of which there could be many. But this also shows that we can clearly do this for string systems. We should be able to do the local events thing for string systems. It'd just be a bit tangled up.
Of course, because we can emulate them.
Well, I know that, but I think it would be useful, Max, whether you do it through the Wolfram Model code or some other way, to write something which does this for strings. Does your local multiway system for strings? Because I think there's
we need
much
string emulator. Don't we have one already?
We have a string emulator, yes. I'm just saying you should put it together.
Well, I mean, if we have it, why don't we just use it?
Well, I know. I'm just saying, just write code so that you could just give your system, write a version of your code so that we just feed it the inputs for the strings, and it just does the right thing, including showing visualization where it looks just like this, basically. Although inside it's using hypergraphs. But the visible version of it just uses strings. Okay. Well,
sorry.
All right. I think it's time for us to wrap up here. I mean, this is the whole concept of local multiway, global multiway, completions, et cetera, et cetera, et cetera. I mean, these are, these are very, powerful, interesting, and abstract concepts, which it's not totally surprising are, I mean, this, to me, the fact that these two potential interpretations of quantum mechanics seem to be converging, which I'm sure they're going to, is really a very, it's an important fact that there are these two different ways of looking at it, which are not yet proved the same, but I bet they will turn out to be the same. Now, unfortunately, the visualization of multispace remains complicated. And I think we have to do this case, and maybe Max can try to get that working, the case of Turing machines. We got to be able to do because that case, our branchial space will be tolerably simple. Do you agree? I mean, because there's only one activity at the position of the head at any given moment, I think that there will be some continuity between states, between space-like separated states, and so on. Do you agree? And that therefore this picture of multispace, in which you can think of it as ordinary space-like space with kind of bubbles of branchial space, is going to be reasonable.
Well, I think we should just fix the Turing machine emulator, and then we can just use hypergraph tools, but we would understand what we should expect to see in them, because
see, I want to make a meta comment about that very process. Okay, my little effort back in the 1980s to make graph-based programming, a graph-based programming environment for parallel computers, this is the realization of that. The very fact that we're even considering using hypergraphs internally, essentially compiling a Turing machine to hypergraphs to run it, is a sign that that idea is working.
I think it is working.
Yeah, I know. But Max, one of the points about that is that means because these hypergraph things can be run deeply in parallel, that gives us a way to essentially imagine compiling things to, it gives us a sort of practical environment for massive parallelism, so to speak, except that we don't yet have an implementation of hypergraphs in parallel. Go ahead. Yeah.
Well, to be honest, I still understand why can't we have automatic parallelization like that in just ordinary Wolfram language. If we just remove all non-functional parts from it, so that every variable is a constant, and every part of an expression is separate and has no side effects, then we should just be able to parallelize each part of an expression independently.
Absolutely. Yes, absolutely. In fact, in SMP back in 1979, it even had an attribute for every function that was called, I think it was called something like para, which said whether the function could be evaluated, in parallel. So something like compound expression clearly doesn't have that attribute, but otherwise it has that attribute.
Well, that would be extremely useful, because that would give us multi-threading, essentially.
I know. Well, I had it 40 years ago. except that it was only partly implemented back then.
Well, I can imagine 40 years ago, it would be much less useful than it is now.
Well, there were multi-CPU systems. They were just very heavyweight.
Well, exactly. So it's like you need special kind of system, and then communication with CPUs was slow, I imagine.
Right, but then
now there's no downside in doing multiple threads, essentially.
Well, I understand, but so the reason that I was thinking about graph programming was for the connection machine computer, which had 65,000 processors, and where, at least in theory, the communication overhead was low. But I mean, I actually have to say it's kind of nice that even though, through not having done anything on this project in 40 years, or nearly 37 years or something, it seems like the idea that one might be able to use, graph-based programming for parallelism. Yeah. Anyway, well, okay, fair enough. All right. Well, we should wrap it up here, and we will continue another time, and look forward to people local and on the live stream in the future. As people may know, we are in the middle of our summer school. We just finished week 0 talking about physics project, and we're about to start our main summer school. So we may be doing a few less live streams, although we might be doing some wild and interesting live streams next week. I'm not sure exactly. And take it from there. Okay, well, thanks. See you all soon. Okay, bye-bye.